Engineers didn't argue, they didn't debate, they froze the entire system within minutes. Not because the system failed, but because an AI had just approved a firewall change that looked completely normal. And at first, no one understood why that decision mattered. This system was designed to remove friction from network security operations. A machine learning model analyzed firewall configurations, optimized traffic routing, and recommended rule changes across a distributed cloud infrastructure. It wasn't experimental anymore. It was already deployed in production environment, handling live traffic. The goal was simple: reduce human bottlenecks in repetitive security decisions while maintaining stability. At first, engineers treated it as a decision support system, but over time, that changed. Most recommendations were accepted by default, not because engineers stopped caring, but because the system was consistently correct. And that trust slowly became the foundation of how infrastructure decisions were made. Until one recommendation appeared that didn't stand out technically, but felt slightly off in context. A firewall rule modification involving a very used inbound port. The system labeled it low risk, performance improving, and safe for deployment. Nothing in the matrix suggested danger. It looked like every other optimization request. But one engineer paused, not because it was wrong, but because something about it felt incomplete. The rule proposed allowing inbound traffic through a dormant network port. The AI justified it using latency improvement in edge case routing scenarios. On papers, the improvement was measurable, but when engineers checked historical data, that port told a different story. It had appeared repeatedly in past security scans, not as an exploit, but as a reconnaissance target. Multiple external scans had probed it over time. No breaches, no incident, but repeated attention. And in security systems, attention itself is often meaningful. Engineers pulled historical logs, scanned patterns, and abnormality reports. What they found wasn't evidence of compromise. It was evidence of interest over time. The AI system, however, treated this as a low-weight historical noise. Its objective function prioritized performance gains, latency reduction, and routing efficiencies. But it did not strongly weigh long-term adversarial scanning patterns, indirect exposure signals, and contextual threat history. So the recommendation was technically valid, but security context incomplete. And that gap changed everything. The engineers reran the model decision log. The outcome was consistent, and they approved the rule. Not because it was safe, but because the model was optimizing the wrong thing. And at this point, the question was no longer, is this rule correct? It became, should this system be making these decisions at all? A manual override was prepared. The deployment was halted. The firewall rule never reached production. No traffic was changed, no breach occurred, but the system was immediately flagged for architectural review because this issue was no longer isolated, it was structural. The real risk wasn't failure, it was plausible correctness. The AI produced recommendations that looked reasonable, improved performance, passed validation checks, and matched historical success patterns, which meant under normal workload pressure, it likely would have been approved automatically. And that's where the danger existed. Not in obvious errors, but in silent, optimized assumptions that bypass human skepticisms. The issue wasn't that the AI was wrong. It was that it was precise inside a narrow objective. It optimized performance, but security is not a performance problem. It is a contextual, adversarial, and historical problem. Humans saw pattern-based risk. The AI saw isolated data points. That mismatch is the core design gap. This pattern is not well. AI systems now manage firewall rules, cloud scaling, access policies, and routing decisions at a speed humans cannot manually audit, which means small reasonably gaps can scale silently, not because AI is unsafe, but because optimization and security are not the same objective. And the real challenge in modern infrastructure is making sure those two don't drift apart. Subscribe for more real-world AI investigations, where systems dictate the signal and humans uncover the truth.